Applications using artificial intelligence are increasingly driving our global economy and influencing the way our society works and interacts. This market shift is expected to generate a tremendous need for more bandwidth with lower power consumption and lower cost in the supporting AI compute and networking infrastructure.
Much larger CPU and GPU clusters are going to be needed, as well as architectures that are much better at utilizing the resources. Architectures like compute disaggregation and memory pooling. And these architectures will require a compute fabric with much better I/O bandwidth and reach. Today, compute fabrics do use electrical I/O, like copper interconnects. They offer very good bandwidth density and low power, but they have very short reaches, less than a meter, which is way short for future emerging architectures. On the other hand, we do have optical connectivity in the form of pluggable modules that are used in data centers. But these solutions, while they have very long reaches, are at a cost and power levels that are way too high and not sustainable for the AI scaling that we need into the future. We need a solution that allows us to extend the reach at low power and high bandwidth, and that's where OCI comes in. OCI is an optical interconnect technology that can meet the I/O needs, the interconnect needs of emerging compute platforms and architectures. The solution would be optical interconnects co-packaged with CPUs and GPUs. They will offer much better bandwidth at high energy efficiency, low latency, and longer reaches. These are the qualities that are going to be required for future scaling of AI infrastructure. Intel developed a 4 terabit per second bidirectional, fully integrated OCI chiplet based on Intel's internal Silicon Photonics platform. It will provide the bandwidth, the density, and the power that are required to meet AI workloads in the future. This OCI chiplet contains a photonic integrated circuit, or PIC, that has on-chip lasers and optical amplifiers. It also contains an electrical IC, or EIC, to drive and control the photonic devices. And it has a path to incorporate detachable optical connector. OCI can be co-packaged with CPUs, GPUs, IPUs, and system on a chip with high bandwidth demand. Our first implementation paves the way for multi-terabit per second optical connectivity that have much better shoreline density and reach than copper. At OFC 2024, we demonstrated an OCI chiplet that is co-packaged with an Intel concept CPU, running error-free traffic over fiber. This first implementation is a 4 terabit per second bidirectional chiplet supporting 64 channels of 32 gigabit per second data in each direction over tens of meters. Beyond this first solution, we have a roadmap to scale to 32 terabit per second per chiplet. So the single PIC inside our OCI chiplet is a complete optical subsystem enabled by Intel's unique capability to integrate DWDM laser arrays and optical amplifiers. They have much better reliability than traditional indium phosphide lasers. We have shipped over 8 million similar PICs with greater than 32 million lasers that are now in the field. The data coming back shows that we have industry-leading reliability.
Intel is ready to enable the industry with our field-proven Silicon Photonics platform, providing high-performance, highly reliable integrated photonics solutions to make AI everywhere possible. For more information on this and other Intel Silicon Photonics solutions, go to intel.com/Silicon Photonics.